So hello, my name is Maciej Szmigiero. I work at Oracle at Linux Virtualization and Security team, which is actually part of the Oracle Linux organization. In terms of my upstream work, I usually work at KVM and QEMU. In terms of upstream stuff, I'm the maintainer of QEMU VM bus support and also of QEMU HV balloon driver, which is kind of like a VirtIO balloon, but using the native Hyper-V Windows protocol. But this talk is totally unrelated to Windows. It's also about mainly QEMU, but it's related to live migration of the device state. So what's the current situation here? In terms of the current live migration in general is mostly done using a single main migration channel. So there is only like the main migration channel, and all the data which needs to be migrated between the source and the destination QEMU has to go via this single channel. Obviously, that's not very good because, well, it doesn't scale very well. And we have this is especially problematic during the so-called switchover phase. So for people who are not, let's say, live migration specialists, basically the live migration in so-called pre-copy mode works that way that the source QEMU transfers as much as possible to the destination QEMU. It switches the virtual machine, which is still running by this point, into a state when it basically logs all the data, dirty data that it has changed, and then it tries to copy those data too. And at some point, the count or size of this remaining data is below certain limit. At that point, the source VM is stopped and the remaining data is moved to the destination QEMU, which then the VM is restarted, or you better say resumed at the destination QEMU. The main data that needs to be transferred is obviously the guest RAM image, but this is not the only data that needs transferring. Also, the state, or let's say, all the what's in the actual QEMU devices, both the devices that are emulated by QEMU, and in some VMs you have the device which were passed through from the host, usually called VFIO, and that's also can have their own state. And here the talk is mostly about the state of those VFIO devices. So using a single channel in 2024 is not very good, because you obviously have multi-core SMP systems, and single channel usually uses only one core, one CPU. So whether this is a theoretical problem or the practical, there are devices which have very large device state, which normally, if we have like emulated QEMU devices, their device state is really tiny, so their transfer times is not really a big issue. But for some devices, this is really a major issue. For example, there are some VFIO SmartNICs. Those SmartNICs are basically the small computers which are separate from the main, let's say, main server or main computer. And all those devices state has to be transferred to the target device. Obviously, you also have GPUs which have their own video RAM, which could be huge. So I'm not a GPU specialist, so I might be wrong here, so sorry for this. But I think that the problem is very similar on the GPU side. So what's the example of that kind of device? This effort was developed against a Mellanox, or NVIDIA those days, Connect X SmartNIC. And this device has 128 gigabytes of RAM. This is not a RAM on the host, but the device has its own RAM. As you can see on this, under this heatsink, is basically you have like a small computer, or pretty major computer with 128 gigabytes, and all those has to be transferred to the destination. And this, even in the small setup, this results in like hundreds of megabytes of device state per VF. This device, by the way, could be divided into virtual functions. So you can emulate like 4 different network interface card from one device. It can happen, it can support even more, but this talk is about one up to 4 for the reasons I will present in later. So why this talk was developed against this card, and the measurement will also be done against this card. It's most of the optimization are pretty generic and could be applied to any similar device or any device with the large device state, and some even are could be applied to any device state transfer. So we have already a kind of we have already a special framework for transferring transferring migration data via multiple channel. This is called multifd, and it was introduced in late 2017 in QEMU 2.1 by Juan Quintela. I hope I'm not mispronouncing the name. And he said that the migration stream becomes CPU bound by about 10 gigabytes per second, which is slow by the current data center NICs, which are at least 100 gigabytes per second, and there are like 250 right now. And also there is the issue is that this multi-FD is only for RAM transfer. It cannot do any kind of device state at the current its current state. It also simply what it does, it basically queues all the RAM pages which need to be transferred to channel threads, and those only this sending and receiving actually happens in parallel in those threads. This is very easy to implement because basically reading and writing guest memory is simply reading or writing to some QEMU host virtual address, so it doesn't need any kind of specific locking. There is some problem with synchronization, but this is like a minor issue in comparison to extending it to device state transfer. So another, to be clear, the metric that this talk is about, and which is we are trying to optimize here, is to reduce the downtime. The downtime is basically the time that the VM is stopped. This is the time when the source has decided that it needs to switch to the destination, and this remaining data is transferred. And after this time has passed, or after all these things are done, the VM is stopped. And for how long this is stopped, that's called downtime. So what kind of problems we have? We have the problem that if we have a single migration stream for all these multiple devices, then obviously introduces interlocking between different devices, because those devices are saved and loaded in order as their device state is being transferred in this single main migration channel. So if we have like a multiple VFs, then obviously it means that there is no parallelization between those VFs. They have to happen sequentially. You can theoretically improve this situation. You can call it fix it by decoupling the data transfer from actual reading and loading. But this will be like a partial solution. And as far as I know, nobody has proposed anything like this right now. And also not the actual, let's say, loading and reading also not only happens on the QEMU side, but also we have the device firmware and the kernel driver. And until recently, the kernel side wasn't even pipelined. So when the source QEMU was reading from the file descriptor, the device wasn't actually providing the data state wasn't read from the device. And so basically, only recently, there has been a part-set merge like a year ago by Mellanox or NVIDIA that introduced double buffering for at least this Mellanox VFIO driver. So now the reading from the devices can happen in parallel with the QEMU reading from kernel. This is already upstream. And obviously all the QEMU improvement wouldn't help us much if we have like a bottleneck in the device or the kernel side. So you can argue that all those changes has to happen, let's say, sorry for the pun, but in parallel with kernel changes. So the current, how the currently QEMU does, what kind of channel it receives is based on the basically a heuristic based on the early data read from the channel. If it matches some magic number that this is the main migration channel, it's if it's not, that is main migration sorry, if it's not, then it's the multifd channel. That's obviously not very flexible. So the first version of the patch set actually introduced some kind of channel headers. This is not actually my design, but also from Avichai Horon from NVIDIA, that introduced an explicit channel header which says what kind of channel this is. Unfortunately, this wasn't very well received upstream, so for now we have to live with extending the existing migration bit stream instead of, let's say, ordering this. So the first version of the patch set also has a dedicated device state transfer channels. So there was basically a set of channels dedicated to sending device state data, and different channels send only RAM data. This, from, let's say, basic test, it shown that it did improve the downtime sometime, about 14% improvement. But at the same, the theory here was that since the device state channels don't transfer RAM, they don't have to participate in the RAM sync process, which is basically a kind of like a synchronization point between those multi-FD channels. But at this time, I didn't have a automated testing tool, so all those tests were just done very, let's say, primitively. So I had to develop some kind of tool when I could do more reproducible tests and find a way to actually remove those channels because they are kind of unwanted. It turns out this is actually, it was possible to have like the same performance with shared channels, but the actual one of the problem is that if you have too many multi-FD channels, then apparently there is not only you don't get benefit, but apparently things actually getting worse. So you basically have to tune the number of multi-FD channels to your workload, which is not great because you don't want to have that kind of like a manual tinkering to have a good performance. So at some point, probably it would be good to understand what's the problem here. But the good thing is you can have the same performance without this shared channels. Sorry, without this dedicated device state channels. So they were removed in the next version. So what's the current design? There is a one-to-one mapping between threads and number of VFIO devices. That's both on the loading and, the reading and the restoring loading side. So there is a reading thread that reads the device state from the particular device. This is, as I said, per VFIO device, and then this is queued for the next free multi-FD channel to actually transfer to the destination. And on the loading side or receiving side, you have there is a thread that takes those buffers, and when they are ready, as there is a problem with the current firmware and kernel interface, that those buffers has to be restored in order. So once you have all the previous buffers received and loaded, then you can restore the next one. So we have to have a kind of reordering thread in order not to block other devices and not to block the receiving multi-FD threads. So because of this buffering, there is some kind of let's say, almost unbounded. It's actually bounded by the total size of device state, but this wasn't really well received during the patch set review. So there is the next version had actually number of when the administrator can configure the maximum number of the buffers that are in the destination not yet loaded. So if this is exceeded because, for example, there is too much reordering on network, then the migration will basically fail. So there are quite a few threads in this design. So in the current parsed version, those loading threads are in the multifd managed thread pool. It's technically possible to use actually fewer threads than devices, although this will almost certainly negatively affect performance, so it's not a good idea. The details are still being discussed with the community right now. The problem was that QEMU did not have like a generic thread pool. The only thread pool in utils was for AIO, and this wasn't possible to directly reuse for just generic worker threads. My last attempt actually introduced a generic thread pool, but it was suggested that it might be better to actually reuse the glibs ones instead of creating a new generic thread pool in QEMU. We need to have some kind of extensions for this thread pool. For example, neither the QEMU AIO nor the glib one has a wait function, which basically waits until all the threads have done its work. So it might be a good idea that's still being discussed, whether to actually add this new method first to glib, to this G thread pool, and then use it in QEMU, or to open code in QEMU. That's about the loading thread. Rest of the threads are still managed by the device itself, which is, well, it's unclear whether actually porting those old threads to thread pool has any sense, because it's basically one call in the code. So probably the number of boilerplate code would exceed any kind of benefit. So this is like a debatable whether this makes sense. So there is also another thing which is not with parallelize, which is the device state change. The VFIO devices have some states when basically tell the device what they can do. For example, whether it can actually run and produce a dirty data, or it can, for example, has been stopped. So only one of those device state changes has actually been parallelized, like happen in a different thread. Rest of those basically happen still in the main migration thread. So for devices that do a lot during this state changes, it might be good to have them in a separate thread too. So there is also a problem that, for example, basic VM state also needs to be loaded in the main migration threads, because it uses the main core QEMU address space methods, which then basically explode when they are called from some different thread. So this also could be fixed long term, but by having them thread safe or reentrant. So that will probably give also some more parallelization, so lower downtime. So let's go to the benchmarks. That's basically the source machine. The configuration of the VM is up to 4 VFs. Unfortunately, due to the limitation of the setup, I wasn't able to test more than 4. It's up to the issue with dirty tracking with those devices, that they support up to 4 dirty tracking or live migration up to 4 VFs. If someone wants to have more than 4 VFs during a VM, it has to rely on basically on machine dirty tracking, which is only possible on either on AMD machines or Intel machines from Sapphire Rapids, I think so. But unfortunately, this machine doesn't. It's too old for this. So up to 4 has been checked. That's the configuration. It has about 100 megabytes of device state per VF, and the benchmarking methodology was running a multiple runs of the same VM, because you have to basically catch the VM in the situation when it's idle. Otherwise, you are measuring not only device state transfer performance, but also the performance of the RAM transfer, which is wasn't the point really of this exercise. And the guest wasn't restarted between those runs, but obviously it has to be restarted or launched again if we were to change the configuration of those guests. For example, change the count of the VMs. Sorry, VFs, not VM. It usually took about 30 live migration for downtime to minimum downtime to stabilize, but I did like 70 or sometimes even 100 just to be sure whether I'm not missing something. So with 6 multi-FD shared channels, that's basically the downtime improvement with this patch set. As you can see, basically it scales more than linearly with number of VFs, which is I hope it will be at some point we reach a state when the device transfer is almost, you can, for example, transfer 4 VFs at the same time as 1 VF because there is no bottleneck on the transfer and loading side. But it's not, we think it's not only about the transfer or QEMU side, but it's also on the device itself that it's not internally parallelized as well enough as it should. So, but it's still, we think that, let's say 67% improvement with 4 VFs, it's worthwhile as a starter. And you can see that it doesn't really break anything, and it's a small improvement with 1 VFs, but it's good that there is no regression, because that's usually what we are worried when there is improvement that only touches the how things scaled. That it might improve the scaling, but usually often it breaks the small case. But in this case, you can see that the small case has improved a bit even. So as I talk, there is some issue with number of channels that you have to tune it yourself. You can see that this is kind of counterintuitive, that with more multi-FD channels, you actually get worse performance, especially on the median and the 75th percentile. You obviously you want to have like as wide, let's say, good performance band as possible, and you can see that basically the performance roughly stays the same to about 15 channels. Above that, you can get it. You can see that it gets worse because this additional channel not only don't bring any benefit, but also actually cause some issues. For example, slow things down by extra unnecessary locking or so. So that's something that we would like to also eventually work on to be as count of channels independent as possible. So what's the status of the patch set? The version 2 has been posted. Version 3 will be posted soon. So hopefully this will make QEMU 9.2, but we'll try as much as possible, but this is like our target right now. There are some also issues with current QEMU migration code, because it's basically a sync code that doesn't return to the main loop until everything is done. That severely makes it harder to introduce any performance benefits. And also on the kernel side, we would love to have a like unordered VFIO device state loading that would simplify QEMU side a lot, but this is not current state, and this would require actually changing the VFIO user space API, so it's kind of hard to do. Obviously, I would like to have like a generic parallel VM state transfer, but this is also very far in the future. I've been also asked whether it's possible to introduce the live stage device state transfer, which is the state that doesn't impact downtime when the device is still running. That's something we have also on mind, but it's also, like, let's say, a very far future direction. So since we have only 5 minutes remaining, I will ask for if anyone has any questions. Yes.
Thank you. So for that one VF numbers you report here, how many channels you're using?
This one?
Yeah.
6. It's 6 channels.
Oh, it's all 6 channels. Okay.
Right.
Okay, I see.
Because you can see that this is the lowest downtime. I actually, I think that if you go below that, you get worse numbers. You start getting worse numbers once again. That's why it uses 4. Okay. Sorry, 6 channels.
Okay, and another question is, so why do you want to listen VFIO device state because not ordered? Because I mean, the VFIO device state is just a black box to you, right?
Yes.
But why you care about the ordering?
Because the device needs to be loaded. Device needs it to be loaded in order. Otherwise, the device would basically fail the migration. That's the problem currently. We want the device to accept it in any order, but the current device and also current VFIO user space API says you have to load it in order.
It's a stream, right? It's
a separate buffer. It's a stream, but you cannot just take a chunks of this stream and reorder those.
Yeah, that's why it's a stream, right?
Yeah, but if you send it by multiple channels, right? Then those chunks can get reordered if they arrive on a different channel in a different order.
Okay, I see.
It's not only parallelization, like you have multiple devices and you have like send data from those devices into separate channels. You also take data from one device and send it on the multiple channels.
Okay. Thank you.
Naively, I just don't know. How is there 100 megs of device state per virtual function?
Basically, those SmartNICs have like, not only there are full computers in itself, they basically have a lot of offloads. They track the state of, for example, IPsec, state of network connections of the host, and that's a lot of data. And I think those devices that we are talking about, they also do RDMA in InfiniBand, and there is a lot of state related to this.
So you have multiple channels for transfer the virtual device state. Is this transfer data traffic mixed with the RAM traffic? Or?
Exactly, that's shared channels. That's what they are. They mix the RAM transfer data with the device state.
Okay.
That's currently only happening during the switchover, which is the VM is stopped. I've been asked to also look at improving those transfers during the VM is still running stage, but this obviously wouldn't touch downtime. So there is like a little, let's say, performance sense of this is limited. You will obviously have a probably quicker migration time, but the VM is still running, so it doesn't matter that much.
So so you show that there's optimal number of the queues for transfer the device state. So I think if when you open a new channel, there must be an overhead. This overhead may also offset the performance benefit when.
Exactly, that's what happens. If you have like too many channels, your overhead starts to exceed the benefit, basically.
Yes. So thank you.
That's something we'd like to, not happen, because we would like people to just stuck with the default configuration, which I think is 15 channels, and it might not work 100% best, but I think it should work at least the best possible for 15 channels. So we want to have this like a performance band or performance set of performance configuration to be as wide as possible.
Okay, we are out of the time. Thank you.
Hey.